In this video, I will show how the constraint programming solver is able to discover a solution and what the computation is happening behind the scene. And so this is what we need, is a search component and a fixed point algorithm. As I said, by default, we will explore all the possible solutions. And so we will explore a search tree like this. At every level, we pick a variable, we decide all the possible values, and then we try one at a time, and we will explore this search tree, for instance, using a depth first search algorithm. Okay, so we will visit that one here, then this one, 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 and this one, and this one, and this one. And eventually, if you discover that one of them, I come back. Every time you discover that something is unfeasible, you backtrack and you try the alternative path. And if you are lucky, here, for instance, you find a solution and you can stop. Or if you are looking for an optimization problem for the best solution, then you need to continue until you discover the best solution and you prove that it's the best one. If you focus on feasibility, you will use the constraints to prune the unfeasible solution. And what we mean by pruning, I already said that in the previous video. What I mean by pruning is eliminating all the values that cannot belong to any solution. So inside the implementation, you will have a search component and you will have a constraint store component that I represent with these two rectangles. The search component and the constraint store will interact very closely. So the search component will pick one variable and say, I want to try this value, for instance, the value 0 for the variable x0. Okay. And then the constraint store now has to act based on this new information. And this corresponds exactly to a branch here in my search tree. You make an arbitrary decision. You take, let's try this value 0 for the variable x0. What the constraint store will do is answer to the search success or failure. Okay. In case of success, then the search can decide the next decision at the next level. And it will say, I will pick the next variable and try the value 2, for instance. And then the constraint store may say, no, this one, sorry, I cannot find a solution with this value. It's a failure. And so in that case, the search will need to backtrack. Okay. How this happens, how the constraint store is able to answer, yes, you can continue and try another one, or no, it's a failure, you should backtrack, is by using the fixed point algorithm and all the constraints. So if I split the view and I dive inside what is happening inside the constraint store, inside the constraint store, I have the domain store here. And the domain store is really all the variables and the domains, the possible values that are still possible for these variables. And acting on the domain store, you have all the constraints. And the constraints are really the objects that you have stated in a high-level model in a declarative way in your model. So these are the constraints of your problem. And the constraint of the problem will act directly on the domain store. They will really be able to remove impossible or unfeasible values from the domains of the variables that are contained inside the domain store of your problem. What the constraint should be able to do is first feasibility checking. And so it should be able to answer, do you think that you might still find a solution for this specific constraint? And if the answer is yes, it should also be able to answer to the pruning. The pruning means please remove the value that you consider as infeasible. And of course, it really depends on the type of constraints. And these two blocks are really algorithms that implement the constraints. Okay, we call them pruning algorithms or filtering algorithms. I already mentioned the fixed point computation. The fixed point computation is really the algorithm that is triggered when a branching is happening. Then every constraint one at a time will act on the domain store to remove unfeasible values. Okay? And this is the fixed point algorithm. The fixed point algorithm, a naive implementation is this one. Is you will repeat until success or until you have nothing else to do, until no constraint can remove any more values from the domains of the variable. This is the stopping criterion. But as long as you cannot do that, you pick one constraint, you check, is it feasible? If it's not feasible, you return immediately failure. Otherwise, you apply the pruning algorithm that I just mentioned before of this specific constraint. Okay? And you repeat for every constraint one at a time until you have a stable situation, which means that no constraint can remove any value from the domain of its variables anymore. This is why it's called fixed point. Okay. So the search component will add branching constraint. For instance, x0 is equal to 1. So you branch and you add a constraint. And then the constraint store will trigger the fixed point algorithm. And it is the fixed point algorithm that will answer back to the search to say, I think I'm still feasible, or I think you should backtrack because one of the domain, for instance, is empty, which means that there is no solution. Okay, so when is it exactly executed, the fixed point algorithm? It's executed after every branching decision. So you take a decision and then you trigger the fixed point. You take a decision, you trigger the fixed point. Every time you trigger the fixed point computation. So it will be executed exactly once in every node of the search tree, this fixed point algorithm. Okay, but the solver will decide to execute it by itself when you add a constraint. Let's study a problem that is quite similar to the Sudoku, which is the 8-queen problem. In the 8-queen problem, well, here it's a 4-queen problem, you need to place n queens on a chessboard such that they do not attack each other. And as you know, 2 queens are considered as attacking each other if they are on the same lines or the same column or the same diagonal. So let's first discard at least one type of constraint, which is the queens placed on the same column by introducing one variable here for every column that will represent the row on which you will position this queen. For instance, here I have q0 equal 1, which means that I place the queen here. Okay, you get it? Okay, once you have that, you can state all the constraints of your problem. Like this, you say for every pair ij of queen, they should not be on the same okay, qi must be different from qj, and they cannot be on the same, what I will call left diagonal or right diagonal. Okay, these are the 2 constraints here. Once you have added all these constraints to your model, you press the run button, it should discover a solution for you. So let's see how it happens. Okay, and so this is, for instance, one possible feasible solution for the 4 queens problem. Okay. I will detail in another video really the implementation of this problem using Java and the solver that we'll use for this course, which is called Mini. But basically, the high-level ingredient that you need is a solver, of course, a set of variables, okay, and also a domain. And the domain is the range of possible values for these variables. Okay, like this. So this is really the domain. It's all the range of values that you can imagine for these variables. And these are the constraints. So exactly in the pseudocode, you have a double for loop. You will post binary constraint for every pair of variable qi for the queen I and the queen j, like this. And this will prevent this and the left diagonal and the right diagonal constraint, like this one. Okay? And then you have the search component. Here, I really consider implementing the search by myself, but it's not at all mandatory. In this search, I'm really making manually the decision of picking the next queen that is not yet decided and decided which value I will try left here. I'm really adding the constraint to the left. And then in case of unfeasible solution, I try the alternative, which is removing the value v from the domain of this queen to the right. Again, this will be more detailed in another video where I explain this code of the n queens problem. Of course, you don't have to implement this branching manually. You can use a default search if you want. If you want to implement it by yourself, it is a little bit less declarative programming, of course, because you open the box and you implement the recursive procedure for discovering solution yourself. But you don't have to do that. Again, you can use a default search that will make the depth first search for you. Okay, and so what happens is that the current state represents here, this is the constraint store and the domain store. It's represented here visually. You take a decision, q0 equals 0, which means that you place the queen here. And as a consequence, all the other constraints will be triggered. and will remove unfeasible values from the other domains. And so they will become red, like this. Then you try the other one, like this, and you discover, for instance, that it's unfeasible. You see that the domain here of the queen 0 is unfeasible now. And so you backtrack, and you say, this was not a good solution, okay? Queen 1 equal to 2 is not a solution. I will try something that is not equal to 2. Okay, and so you try the alternative not equal to 2, which means that there is only q1 equal to 3 left. You propagate this decision again, okay, like this. Does it work? Yes, it works. It looks like it works. So you try the other variable for queen 2. You have no choice for this one. As a consequence, because you have placed this one here, you will have to remove this one. And you discover that there is a failure. And this will be discovered by the fixed point at this level. So all this computation was triggered by making this branching decision during the fixed point computation. And since it's infeasible, you backtrack. You need to backtrack because there is what we call a domain wipeout, which means that one variable, the queen 3, has no possible anymore. So you cannot branch anymore here. Okay, it's unfeasible. So you need to backtrack. And then you backtrack. So you backtrack from here, you backtrack from here, and then you are here. Okay, so we backtrack. We revert all what we have done before. We come back to this situation. And we say, no, the queen 0 must be different from 0. So we put this one in red. But then we need to decide again a value for queen 0. And so we take, for instance, this one. Queen 0 is now equal to 1. So we place this one here. As a consequence, you will propagate this. You will propagate this. Okay. And you will propagate, of course, this and this. Okay. So all this become red. You take a branching decision. Queen 1. No, it's not over yet. Here you have no choice anymore, so you will place one queen. Okay. The fixed points will be continued. It will remove this one, this one. Sorry, it will remove this one. Okay. But then it means that you place a queen here. Okay. If you place a queen here, this one will be removed. This one was removed because of that one. And so you have also, again, a domain wipeout here. Okay. Again, it will lead to something that is not feasible here. No, sorry, I'm mistaken. It's a feasible solution in this case that you discover. And so this is the way the solving works. You alternate between branching and pruning. And by pruning, we mean triggering the filtering using the fixed point computation. Every constraint is called one at a time. We ask to the constraint, please remove all the values that you consider unfeasible. And then we continue. Once we have reached the fixed point, you take again a branching decision. And in case of unfeasible solution, you backtrack. Okay, I hope it's quite clear for this. And so you can have a success answer from the constraint store, or you might have a failure answer from the constraint store in case you have a domain wipeout or one of the constraints says I'm unfeasible. In the next video, I will show another example, which is quite famous in constraint programming. It's a puzzle that is called a send more money problem.